Cool. Hello, everyone. Hope everyone's having a good climate informatics and is ready for our final day. My name is Guillaume Couéron, and I work on diffusion models for weather forecasting in ENIB Paris in Claire Monteloni's lab. So I have the pleasure to take the chair for this session of lightning talks, which are 7 to 10 minutes long. Our speaker will present, and after each presentation, we have time for questions, both via Slido and in the room. So first, we have a talk on Antarctic contributions to global sea level rise by Fiona Turner, but she couldn't make it today, so it's going to be presented by Tamsin.
So this is the work that I mentioned on Monday that Fiona's doing to look at the same data in parallel with different emulation methods. And particular thanks to John T. Ruger, who wrote a lot of the original code that Fiona's been adapting and using. And as she hoped in the slide, I hopefully did motivate, if you saw my talk on Monday, a lot of this work. So basically, if you weren't there, a quick recap: the predictions of sea level rise at 2300, which are shown on the right-hand side in these bars, are really uncertain. Just simple ranges of previous studies, basically, not a sort of a full probabilistic estimate based on lots of models and physics or anything like that, as it was done for the 21st century, which is shown on the left here. So the aim is to come up with probabilistic time series of the Antarctic contribution to sea level rise up to the year 2300. And as I say, we wanted to use a kind of a different emulation method. So you remember in my talk on Monday, I said we had sort of ensembles on the century timescale and then a smaller ensemble to 2300, and that's what Fiona's using here. So there's two different ice sheet models, basically, that are being used. And they ran ensembles that started back in 1950 so that we could evaluate with observations and used a nice space-filling design, a maximum Layton hypercube, if you're familiar with that. I forgot to start my timer, so wave at me if I start getting close to time. And then you'll remember in my study I had about 22 Antarctic inputs that were being varied because I had the century timescale runs as well. In Fiona's smaller ensemble, there's about half that. The majority of these are continuous. I'm not going to kind of go through them, but you can see quite a lot of these are numerical ranges. They're continuous parameters. A lot of them, most of them relate to the relationship with the ocean, which dominates the Antarctic response. So the basal melting as a function of ocean heat, basically. And then we have some things that are relating to the climate state that's driving the model as well. So the initial atmosphere and ocean. So the kind of driving climate in terms of like the emission scenarios, we have quite a limited number to choose from that go to the year 2300 from the CMIP archive. So at the time, the modelers used these 4 general circulation models. And there were just these 2 scenarios, very high emissions, SSP 585, and low emissions 126. And these are showing global mean surface air temperature change over the period that we've got. So you can see the 2 scenarios there and the 4 GCMs for each scenario. And we're using that global mean temperature as a kind of metric of climate, just like in my talk, even though the models are actually driven with much more spatial, regional, complex fields than that. And as I say, Fiona's using random forests. So we have about 1,400 simulations in this data set. At the moment, with my Gaussian process, I'm throwing a few away to make it more tractable. I'm just using 1,000 of those. And so the random forest, the primary motivator for trying it was that it was just much, much faster. But also maybe it might deal with some of these categorical choices that we've got in here, like different data sets or like switches between different parameterization schemes within the model. And potentially might be better at dealing with the kind of asymmetric PDFs that we expect in this field. And as usual, we use just the random forest with the residual from a linear trend. And we're using quantile regression to estimate the uncertainties. It's all in R, that's the package there, quant-reg-forest, to get the uncertainty estimates, which, as I mentioned on Monday, we think is really important to keep the probabilistic framework. Standard sort of 2 parameters in a random forest to tune, M-try and node size, if you're familiar. We train those on 90% of the data and optimize with the other 10% using the same metric that Ilan mentioned on Monday, the continuous ranked probability score, CRPS, and then refit to the whole data set. And then we do the leave one out validation as well as a sort of sanity check on how well it's doing in terms of that coverage that I mentioned, how many of the simulations when you train the emulator and all the rest are within the uncertainty intervals of the emulator. So this is showing leave one out validations at multiple different years through the 3 centuries, so 2100, 2150, 2200 and 2300. I showed the last of those on Monday. And we've got really good coverage. Actually, the lowest here is 98%. So if anything, the emulator's a bit pessimistic. The uncertainty intervals are quite big. Mine go down to 94% instead of 98% here. But generally speaking, you know, all looks quite sensible, and we would rather the emulator was underconfident than over. We can do main effects plots. We can vary one input at a time and keep all the rest fixed. And so global mean temperature, that primary climate variable, you can see I get a similar result in the Gaussian process in terms of this knobble here. And this is basically because we have noisy data. Remember, we had 4 GCMs at low temperature and 4 GCMs at high. And because we're actually forcing with regional temperatures, that creates a bit of funny ordering in the temperature response here. It's not monotonic, basically. So that's a real physical signal because of the simplification of using global temperature. But in general, we get kind of similar shapes to the Gaussian process. This is the different basal melt parameterizations in the model. The random forest can separate those out a bit more, I would say, than the Gaussian process, but the ordering is the same. And then the other ones I said that were important, the parameters that control that basal melt sensitivity, all quite similar. The Gaussian process is a bit more curvature, but more similar uncertainties across all different inputs, whereas these seem to be a bit more linear, but distinguish uncertainties a bit better or a bit differently. So you can see some of the bands are wider than for others. So the projections that we get to 2300 basically look like this. These are different scenarios for SSPs. We have a simple Bayesian calibration, just like I've got in mind just for now, just as a quick first order look, which tends to not only reduce the uncertainties, but favor the lower end of the projections. And sort of particularly shrink the uncertainties for the lower end. And the first century of the projections, just like I showed, tend to, on Monday as well, you tend not to get much difference between scenarios. I showed this, I talked about this in the questions, because you have a compensation of increasing snow as well as increasing melt, where it takes until the second century for the melt to dominate. And then you can get lots of quantiles for things, and her results show, a bit like mine, that you have some possibility of sea level, so mass gain from Antarctica in the first century, but in the last time period you can end up with approaching 5 meters of sea level contribution at the 95th percentile. So that's basically it. We can look at which parameters are most important. We can see how the emission scenarios start to dominate after the first century and go up to high numbers. The random forest gives us smaller uncertainties than the Gaussian process, and a few differences in the time series, as I mentioned as well. So we're looking into why that is and which we believe more, I guess. Thank you very much.
Thank you, Tamsin. Do we have any questions in the room? No questions?
Okay.
Well, no questions on Slido either, so we can move on to the next talk. So next we have Liu et al. From NERLC. Who's going to talk to us about Arctic sea ice.
Hi everyone, I'm Leo. I'm going to talk to you about the reconstruction of Arctic sea ice thickness based on a hybrid machine learning and data simulation approach. I would like to thank my colleagues at NERSC in Norway that I've been working with, and the people of Climate Informatics that allows me present my results here. When I first started my postdoc, I was impressed by the difference in terms of CI thickness that you can see here for the observation on the left and for the model that is developed in Norway, which is called Topaz. And you can see that the global patterns of CI thickness are widely different in the central part of the Arctic, for example. And because most of you may not know those products, I'm having a quick reminder here. So CIS2SMOS is a merged product of two satellites that is that is giving observation between October and April. And Topaz is a model built on HICOM for the sea that is coupled with a CIS model and forced by ERA and Turing with a 10 by 10 square kilometer resolution. And so when we assimilate satellite observation in Topaz, then we can see that we see similar behavior in terms of CI thickness. So there is a clear improvement once we assimilate those data. But the main issue is that this satellite product is only available since 2011, and before the remote sensing observation suffer from high uncertainty and a lack of temporal and spatial continuity. And so in this project, we are asking ourselves if we can extrapolate the benefits of data assimilation to past period when we had no CI thickness observations. And that is mainly so we can have longer historical data to initialize model that use long-term studies, for example. And so to do that, we have two versions of Topaz, one that assimilates CI thickness, which will be called reanalyse, RA, and one that is totally without assimilation, that is a free run. And then from this difference in the model, then we can have the CI thickness bias of the model and use a machine learning algorithm that we will train over this time period that will enable us to predict into the past the bias of the model so we can extend the CI thickness observation, CI thickness time series. And then I will show you a quick validation with in situ data of this extended time series. So I'm going to follow those time steps. And first I'm going to show you the CI thickness bias. So you can see between 2011 and 2022, the free run of the model in blue and the satellite observation in purple. And when we assimilate, then we get the curve in black. And we see that the data simulation improves the CI thickness over the whole timeline and not only for one day, like I've shown you before. And then we get this difference. So we can see that the bias is mostly negative, except at the end of the summer, when bias has been accumulated without data to assimilate. And here you can see the spatial distribution of those biases. So we see that we have two thin CIs in blue over the central part of the Arctic, mostly. And you have two thick CIs in the Beaufort Gyre. And that is in the free run. And that because there are very strong winds and drifts that are pushing the CIs that get trapped in the Beaufort Gyre. So that's a systematic bias, for example, that we would like to correct. And we are evaluating the machine learning algorithm with a baseline that is actually the monthly bias between the free run and the reanalysis that is just applied into the past. I'm going to talk to you about the methods that we are using to adjust the CI thickness. So we take the CI's bias and we use EOF decomposition between 2014 and 2022. Then we get several spatial distribution of the bias and the temporal evolution of the bias that are the principal component. And then for each principal component, we build one machine learning model. And we for today, I'm going to show you results with 8 principal components. For each model, we give a set of oceanographic and atmospheric variables that are also decomposed using the same EOF decomposition. And for example, we use the sea ice concentration, the snow depth on top of the sea ice, as well as the sea ice age and the air temperature from AR5. And then you have the final scheme here. So we use those input data with various variable and various time lags that can be either in the past or in the future. And then we use LSTM machine learning architectures to predict the CI's bias. So now I'm going to quickly show you some evaluation of the machine learning performance during the test period, that is between 2011 and 2013. So you can see the bias in winter for the top row and in summer for the bottom row, between the free run on the left and the reanalysis, the baseline in the middle, and the machine learning and the reanalysis in the right. And we can see that there is a good reduction of the bias, even with the baseline, even if it remains some large error close to the coastlines. And we see that the bias is drastically reduced with the machine learning algorithm here on the right. So now that we have quickly evaluated the machine learning models, I'm going to use it to predict the CI thickness bias into the past. For that, we predict each principal component, then we reconstruct the CI thickness bias, and we add it to the free run of Topaz 4. And then we get this daily field of CI thickness that has been adjusted. So here, until the 1st January 92. And I'm going to show you this time series that is average over the whole Arctic. And you can see for the force data sets, so the reanalysis in black, that is only going up to 2011, the free run, the machine learning, and the baseline CI thickness. And we can see that we do reconstruct the trends that is going on, and we do not introduce any unrealistic behavior by extrapolating outside of our time period. But it's a bit too early to believe in this product, I would say. Then I'm going to show you the evaluation with independent datasets. And here I'm going to focus on upward-looking sonars, and mostly this point, this mold here. And that's the number of observations we have in the Arctic. There are some that should be close to the Fram Strait, but they are quite sparse, both in time and space. So here you can see I took the closest grid points from this buoy here. And you can see in black the in situ data with in gray the one standard deviation. And you can focus on the machine learning adjusted CI thickness that is in orange here between 2004 and 2011. And you can see that we have a clear improvements with in situ data, mostly during summer. For example, here in 2004, or like every summer actually, even if there are still a higher variability with in situ data. For example, here at the end of 2007, which was a special year. But that's one of the challenges that remains when we compare models and in situ data, both upward-looking sonar or like remote sensing observations. I'm going to quickly interpret the reconstructed data. Here you can see the CI thickness distribution for each day. I did an histogram of the data, and the whitest the area, the higher the occurrence. So we can see that there is a gradual transition from bimodal in the early 90s to unimodal CI thickness distribution later during this decade. And we see that there are some trends that have been compared with the literature and are quite similar, but in the free run model, even if the trends are similar, there are still high differences in terms of total quantities. And now I'm going to answer this question I asked first. So yes, we can extrapolate the benefit of data assimilation to the past that I've shown by this reduction in the bias with a quick evaluation with mooring data. And I had no time to show you the remote sensing comparison, but it exists. And, and if you're interested, yeah, I would like to conclude with the fact that this innovative approach can be implemented for other variables and other models. And if you're interested to learn more about these projects and my results, I will have a preprint available soon. So don't hesitate to ask me questions or like to get my emails and ask me questions later. Thank you.
Thank you, Leo. Are there any questions for Leo? Okay, I have one question actually.
Yeah.
Because you bias correct your model by training towards a data assimilated model, now that you have a better model, what do you think happens if you do data assimilation on this newer model?
So that's a natural continuity of, of the project, at least something that we planned. So we need uncertainty to predict the uncertainty as well, and then it would be able to assimilate it again. And we should converge towards the same, not the same CI thickness, but at least we should converge towards a common CI thickness in the end.
Between the old model that has assimilated data and the new model that has assimilated the data?
With we should converge to the CI thickness that has been corrected, but I guess it would be a slow process that may need several iterations. I think so.
Okay.
But I think the relation between the CI thickness and how it impacts other variables in the model is not clear. And that's something we need to look into. Yeah.
Okay, thank you very much. Just as a reminder, you can also send your questions to Slido, even in the room if you wish. Next, we have Ayush from the Finnish Meteorological Institute, who's going to talk to us about modeling snow on sea ice.
Hello everyone, I'm Ayush. I'm a master's student studying computational science at the University of Helsinki in Finland, and today I'll be talking about our work on modeling snow on sea ice using physics-guided emulators. And this was the work that I did as a part of my internship at the Finnish Meteorological Institute with my collaborators Johanna Murhuyadi and Alexei Nemelin. So as we have already seen from the previous presentations, that sea ice forms a very crucial element of the Earth system, and specifically snow on the sea ice regulates the growth and decay of the sea ice, and it has some unique properties such as like low thermal conductivity, which stops the growth, which hampers the growth during the winter, and similarly during summer it regulates the loss of sea ice. And right now, the climate models have a limited representation of this behavior of snow on sea ice, and they use typically fixed values for parameters such as snow density. And the aim of our project was to use these snow process models, which do exist, but they are computationally expensive and are hard to run. And so our idea was to emulate one such model. Specifically, we chose snow model, and which I'll talk about in the other slides, but that was the goal. And we wanted this simulator to be like somehow trustworthy, either through the use of purely interpretable methods like decision trees, or somehow like rooted in physical principles if we could. And in the end, we ended up using regularizations, which had some physics terms from the snow model. And yeah, so this was like the two objectives. Like our first objective is to model the snow density parameter from snow model and compare the emulators that can do that. And our second objective was to explore some physics-based loss functions that can constrain these emulators that we use. Some very brief introduction about snow models. So it was developed already in the late 1980s in the US, and it's a numerical process-based model that can simulate the evolution of snow. And originally it was designed for terrestrial applications, but since then it has been researched in multiple literature and expanded for use on the sea ice. And like any other numerical model, it requires some input parameters, which are like meteorological parameters and topography. And depending upon those input drivers, the resolution can be from kilometers to meters. The main challenge is that like the snow model was written in like originally in Fortran 77, and like it was not at all designed for keeping parallelization in mind, and that's like very slow. However, last year they have like started, they have released they are working on a version which is now parallel, has some parallel capabilities, but it's not available publicly yet. And this was like the setup that we had for creating the training data for the emulators. We selected 5 regions in the Arctic, and we chose these in such a way that they have at least some varying atmospheric conditions, and also some nearby field data if we were in future to compare how well does even snow model work. And we had some limitations in terms of topographical data, like we had a few topography which were conducted from aerial surveys, but we tried to replicate those properties and created some more topographical features synthetically. And these I'll talk about in more details in my the preprint, which will be released soon. And the simulations, they started in, they were 10-year simulations, which were from August 2010 to the end of August 2020. And we had a temporal duration of 3 hours, so that we can capture the properties of snow during the day and the night. And we chose Mera 2 as our drivers here, and these are the features that we used, the input drivers. And they are also the same that we use for driving the emulators. And like day of the year is not explicitly as such required by snow model, but it's for a random forest emulator that we use in the next slides. Yeah, and as we have already seen, like both of these models today, like random forest is typically works very well with these kind of non-linear behavior, and it fits well to almost any kind of data, I think. And we had like 500 trees configured for this. And the other main model that we evaluated was LSTM, and here we had a simple setup of 5 input features which were in the first layer, and like two LSTM layers and dropout layers, and the final was a dense layer. And the physics guided version that we were evaluating had the same architecture setup, except 2 changes: that in addition to snow density, we also predicted snow depth and snow temperature. This is so that we can use those relations in the equations that we have. And the other change, those were the 2 changes. And we compared this with a climatological baseline just to see if these models were even worth it to run. And this is like the main idea behind the physical principles of snowpack compaction in snow model itself. So the idea is that when snow falls, like the lower layers of the snow, they get subjected to increasing pressure, and as a result of which the layers which are in the bottom, they have the highest density. But this is not just purely as a factor of snow depth, but there are also properties such as snow temperature and other thermoconductivity related parameters which snow model does explain. And that's the idea behind how density due to snow compaction is explained in snow model. So sorry for this equation, but it's the idea is that here we have the main equation that explains snow density from snow model as well. So at every time step t, the snow density given by the snow model itself can be explained by this equation, and like as a function of the previous snow density, and the 2 other main parameters are the snow temperature and the snow depth. And so we use this to add a new loss function to a term, which is like apart from the MSE, from the LSTM, that we also compare how well this violation is being treated in the LSTM. Yeah, this is like the main combined loss function. So the total loss function, now we have like the original LSTM loss for all the three variables, and then the density loss from the snow model. And this is like, we have a regularization parameter here. And from our experiments, we found like somewhere between 0.3 and like 0.4 was giving us a good performance. And these are some initial results, and we used leave one out cross validation because the idea was to like be confident if we are applying this to some in an area where we have never trained the emulator before. And so we systematically rotated between the 5 regions to get these results. And so what is clear is that like all the 3 emulators, they perform better than the climatology, but in terms of LSTM and physics-guided LSTM, there wasn't a huge difference, at least in terms of RMSE. It did perform better in like 4 out of 5 regions, but it's hard to say what exactly is making it better at this stage. And this is also another plot where we took a mean of the entire spatial area, and you can see that the physics-guided snow density is matching very closely from the snow model snow density, and this is for 1 year simulation. And also a spatial plot of the snow evolution at a span of 10 days. And what we noticed that the model makes the error in those places where the snow density is higher, and it somehow underestimates, but I'm not sure what is causing that right now. Yeah, and in conclusion, what I would say is that our results show that the emulators did perform better than this climatological baseline, and we were able to emulate the snow model's snow density. And there's a typo and incorrect line that the speed up was not 9,000 times, but the slowest emulator, which was random forest, it gave us a speed up of 9,000 seconds. And the physics-guided LSTM, it performs like up to 64 times faster than the original snow model, which is like a good emulation speed for our need. And adding the physics-based loss term did improve the performance slightly, but it's not very certain yet. And the next challenge is to actually implement this in a climate model or in a larger framework to see how well this works and if the simulation is working well as expected. And thank you very much.
Thank you, Ayush. We have a few questions on Slido. The first is, why did you choose Mirror 2 specifically?
Yeah, like the mirror, like it's not really, we did not consider it during the emulator design, but we just chose it because the previous studies which had used no model itself and not any emulator, they had found that ERA somehow was overestimating the snow density, and so it was just a reason why we stuck to mirror.
Also, Anna asks, did you have any chance to train the model over the whole Arctic?
No, not yet. Like, we are just in the initial stages and seeing if it works.
Okay, last question. Does LOCV perform better than the sequential time step?
Like the performance, it does work well even if we do a time-based splitting explicitly, and actually the performance is much better if you do a sequential time-based split for the same region, which is expected. But with LOCV, we evaluated in such a way that the model had never seen the region at all. So that was like, even though the performance is slightly worse, but it's better.
Okay, thank you, Ayush. Interesting to. Yeah. Okay, now we're going to leave the field of snow and ice, and we're going to go into wind by Irish.
Good morning, everyone. My name is Harish Baki. I'm from TU Delft as a postdoc, doing a postdoc there. This work is in collaboration with Sukanta Basu. He is from USA. He's working as a professor there. My talk is about estimating high-resolution profiles of wind speed from a global reanalysis dataset using TabNet. I see a wide category of attendees here, so I just want to give a background of what are the offshore wind turbines currently deployed. So if you look at the figure, you can see actually how big and massive they have become right now. So the tallest wind turbine currently deployed is standstill 290 meter tall, and it has a rotor diameter of 236 meters. So if you compare, this rotor plane can cover almost 7 NFL football fields. So you can imagine how big they are, and you can see the Statue of Liberty, very tiny, small, lying around, and the turbines almost reach the tall of Eiffel Tower. So what's the big deal about this turbines becoming bigger and bigger? Now the turbines can directly interact with different types of wind profiles that exist in atmospheric boundary layer. So the thing is, different types of wind profiles does have different types of loading conditions and power production for the wind turbines. So we have to accurately analyze what type of profile might have, like we have to analyze what type of profiles might come in the future or in the current state. Previously, due to the smaller size of wind turbines, people usually use wind speed at the rotor center plane to estimate a wind power that can be generated by the turbine. But now, due to this wind turbines become bigger, you have to take a wind speed at multiple levels across the rotor plane, so that that can actually explain how the wind is varying across the plane. You can see that throughout this 230 meter height, wind speed can change drastically. So you have to take account for that as well. So that's the reason the accurate estimation of wind profiles is necessary. So currently, wind profiles, like it's nothing but a wind speed at multiple levels. It's not so easy to even measure. There are only 3 kind of measurement devices can be deployed. One are tall towers, lidars, or SODARs. And you assume that you want to deploy a offshore wind farm at a certain location, but even before doing that, you have to know what kind of wind conditions exist in that particular region. To do that, you have to have measurements, but deploying this kind of measuring device is extremely expensive. And what if you don't find the suitable conditions in the particular region and you already deployed measuring devices? Then it's waste of money. It's huge waste of money. So the next thing is to use some kind of extra empirical equations to extrapolate surface measurements to certain vertical levels. But again, though there are certain equations exist, they suffer from validity up to the atmospheric boundary layer, as well as they need certain variables they do not actually measured by the ground stations. So that can also be ruled out. The next thing, everyone like currently using numerical weather prediction models in estimation of wind profiles. Like you can do a mesoscale model run and get a wind speed at multiple levels. But again, you know that running mesoscale models for a longer time is also not so easy, like computationally. So if you look at a mesoscale model, in that mesoscale models, the wind speeds are governed by like a turbulence and all. They are parameterized in the planetary boundary layers. In the boundary, in that equation, in that parameterization, we only take wind speed vertically. We try to get the accurate wind speeds in the vertical direction rather than in the horizontal direction. Why? Because the horizontal resolution is much coarser compared to vertical direction, so that the turbulence, fluxes, and everything are ruled out in the horizontal direction, but they are accurately characterized in the vertical direction. So in a sense that the wind speed is one-dimensional in mesoscale models. That's what we think. So so the problem now comes into just one-dimensional equations. Like if we have large-scale meteorological features at one point in the from a global model, is it possible to estimate wind profile, like a wind speed at multiple levels? That's what we wanted to look at. But again, so multiple levels in the sense you have to predict or you have to estimate wind speeds at different levels. Then the problem becomes multi-output. So accordingly, you have to choose different kind of machine learning algorithms which have the capability to produce different multiple outputs. So as a proof of concept, we took 34 meteorological variables from ERA 5 reanalysis dataset. So here I only presented which are more relevant to wind speed and atmospheric stability conditions. And as of now, we don't have observations from towers or any observational devices. So we also took wind speed from a SERA reanalysis dataset. These actually have 12 vertical levels of wind speeds. Since, as I mentioned, the problem is of one-dimensional, we took wind speed at a Fino 1 site. This site is very specific. Why? Because a lot of wind energy studies were conducted at this region. And the idea is to, in wind energy community, people usually measure wind speed during either 1 or 2 years, and they correlate for a different kind of years. This is called a measure, correlate, and predict approach. To emulate, to mimic that process, we took wind speed data for 2 years, 2000 and 2001. So we do estimate, we train for 2000 and estimate for 2001. In addition, since we do not have an accurate equation to estimate wind profiles provided by large-scale features, the idea is to see what kind of meteorological features are actually contributing to the two different kinds of wind profiles. So that also need to be estimated. So to account for all of these, we took TabNet machine learning model. This is an attention-based sequential deep learning model. It has a capability to produce multiple outputs. At the same time, it has this attention mechanism. It only chooses features which are more relevant to the output. That way we can explain the physics behind it. So you can do this kind of training and all at one particular location, but the thing is you may have different kind of wind profiles at a different location. Since we took only 12 vertical levels here, if you train the model for 12, then if you have a wind speed at maybe 13 or 15 from a different measuring device, then you have to change the model. Instead of changing the model itself, we wanted to make the model generic across different kind of target data sets. How can we make that possible? So first, we try to approximate the wind speeds using Chebyshev polynomials. So the equation actually says that the wind speed can be approximated by using Chebyshev polynomials multiplied by Chebyshev coefficients. The polynomials are governed by simple governing equations. So in our study, we took fourth order Chebyshev polynomials. The polynomials actually have a physical significance. Why? Because if you look at the T0 actually explains what is the mean of a wind speed, and the T1 explains what is the shear of a wind speed. In the same time, T2 explains what is the parabolic shape. You can see that winds have a kind of curvature in a vertical direction. So that actually can be explained by a T2 polynomial. Similarly, T3 and T4 can explain higher order intermediate wiggles within vertical profiles. So the polynomial approximation is not just an approximation. It has actually a significant physical significance. So the Chebyshev coefficients are simply estimated by using solving linear equations. So once we do that, you can see that the polynomial Chebyshev polynomial approximates the vertical wind speed perfectly. Here I presented 4 types of wind profiles that actually known to everyone in wind energy community. That one is a high shear, low shear, and a low level jet, and the high winds. So throughout this study, we will be talking about these kind of wind profiles because they have a significant influence on the wind energy community. This is a TabNet architecture.
Excuse me, Harish, can you please conclude? We have
okay.
10 minutes already.
Okay,
Thank you.
then this is, I won't explain it, but I'll simply show the results. So you look at the coefficients are not accurately predicted by this TabNet model. The problem here is that the C0, C1 coefficients are like they have a wider distribution, while C2, C3, and C4 have very shorter distribution. That's one reason we think. And the parameter importance also explains that wind speed and the stability of atmospheric conditions are actually contributing to this wind profiles. Yeah, here you can see that two types of predictions we presented here. One is actually exactly matching, and the other one is not well matching. So we want to look at why this is happening. So the main source of error comes from this temporal shift between different types of data sets, that is between ERA 5 and Sierra, since we took that. Due to this temporal shift, since the problem is also one-dimensional, we somehow have to overcome the temporal shift. Then if you have both inputs and targets are exactly aligning and at a particular time step, then the prediction might come really well. That we wanted to look at, and we wanted to train for a spatial transfer learning as well as a temporal transfer learning in the future studies. Thank you.
Thank you, Arish. In the interest of time, we're going to move on to our next speaker, Abhirami from the University of Exeter.
Okay, hi everyone, I'm Abby. I'm a PhD student at the University of Exeter, and my research is also in collaboration with the National Oceanography Centre in the UK, and I'll be talking a little bit about some of the work I've been doing as part of my PhD. So to give a little bit of background, the ocean biological carbon pump is a set of processes that describes how carbon moves throughout the ocean, and I'm personally quite interested in organic carbon. So this is a very general overview of the processes in the carbon pump. So why do we want to understand the carbon pump better? So it helps us understand the ocean's role in the global carbon cycle, so understanding how carbon is sequestered in the ocean and what features or what factors influence that, as well as understanding how certain nutrients are distributed to different marine ecosystems, so something of great interest for us. And so the way that we monitor this carbon transport, organic carbon transport is via a metric known as particulate organic carbon flux, or POC fluxes. And there are several ways of measuring this in situ, which is what I'm interested in. So firstly, we have the most traditional method, which is the sediment trap. So this instrument, which is deployed into the ocean over weeks or months, and basically it collects sediment, which has organic carbon in it, and then you take those samples to the lab, you can get a POC concentration and then a flux from that in a fairly straightforward way. The second method relies on radioactive traces, so 2,3,4 thorium, which has a relationship with biogenic material, and from a thorium concentration you can get to a POC flux from a couple of calculations. And then finally, we have the most autonomous of the three methods, so the underwater vision profiler, which is essentially a camera that takes images of the ocean, and you can estimate a POC flux by classifying what's in the image and then estimating how much carbon those organisms are likely to have. And there are several studies that have been done on these individual data sets, and nothing that really kind of combines all of them together, which is what I'm quite interested in. So if we look at the coverage of the data, the first thing you'll notice is that it is very sparse globally, which is something you find often with a lot of oceanographic data, but especially biogeochemical data. So especially like in the Indian Ocean and around the Southern Ocean, we don't have a lot of observations. We have about 50,000 observations, of which 90% are the UVPs, given that it's the most autonomous. And yeah, so these are the data sets that we are working with, and I want to try and use these to be able to estimate global POC fluxes, and I want to do this using well-sampled environmental driver data sets, so environmental features that we believe to be important for POC fluxes and for predicting them, to be able to identify the importance of these drivers for predicting fluxes, and to also be able to combine the three in situ heterogeneous data sets. So by heterogeneous, I just mean they come from different instruments and different data collection methods. So to kind of give an overview of the model structure, so we've taken some biogeochemical kind of nutrient concentrations, so like nitrate, phosphate, silicate, but also some more physical parameters. And what I will say is that for us oceanographers, but especially the biogeochemical ones, monthly climatologies at a 1 degree grid are as good as it's going to get. So for us, that is a well-sampled data. And so we use those as inputs for our models and train those on the in situ observations that we have. And we tested out a few different types of models, so linear regression, random forests, and neural networks, to then get global POC flux prediction maps. So to just look at what we get, when we train multiple samples of the 3 in situ observations on the 3 types of models multiple times and aggregate those predictions together, what we see spatially is actually quite similar distributions, which is nice to see. So you tend to get higher fluxes around the equatorial regions and slightly higher fluxes around coastal regions, which is what we would expect. We generally see that the random forest performs the best, which I guess is something that we found as a common theme throughout the talks that we've had. And looking at the SHAP values for the random forest models, so the impact that the different features have on making predictions of fluxes. So it's actually ranked in order of importance. So we have the euphotic depth, the depth of the observation, and the temperature as being the most influential predictors for fluxes, which is quite interesting because you hear a lot about, well, you would expect that the nutrient concentrations would have quite a big influence given how the processes work. So that's something quite interesting to see that comes out through the models. However, while doing this research, we sort of thought that given that the in situ instruments, or while the data sets that come from them are so different based on the data collection methods and the calculations to get a flux, we wanted to work with a model that accounts for the differences in the 3 data sets. And so for that, we turned to the Bayesian hierarchical model. So in a nutshell, this allows us to model with uncertainty. So instead of having model parameter point estimates, you have a posterior distribution, so you can get kind of uncertainties from that. You can also introduce prior knowledge into the system. So as an example, physical constraints. So we know that depth has a power law relationship with fluxes, and therefore that power has to be negative, and because we know that the deeper you go, the smaller your fluxes are. So you can introduce those sort of constraints. And there's also the hierarchical aspect, which basically tells the model that the observations that we have are grouped. And in doing that, you can estimate things like measurement uncertainties for each of the instruments, and also things like offsets. So whether one instrument is more likely to give you higher fluxes than others. And the way we can look at it is by saying that you have a true process model, so the true flux, irrespective of the instrument that is making that observation. And then we have at the instrument level, these kind of instrument level models are informed or are distributed and taken as samples from the true process model. And then we say that the observations are they come from the instrument level models. So there's that kind of relationship at the different levels, and you're sort of pulling information from the different instruments to inform that true process model, irrespective of the instrument that you have. And so the work I've done on this is quite preliminary, because at the moment I've taken that process model to be linear, which is definitely not the case. And we're definitely looking into applying sort of more non-linear models, so potentially a Gaussian process model again, which we've heard a lot about in a lot of the talks. But with the models that I have, you can, again, very similarly get global POC flux predictions. And again, you kind of still see those kind of larger fluxes around the equatorial regions and around the coastal regions, which is promising. And looking at the model parameters or the coefficients for the environmental drivers that we have, just by looking at the magnitude of these, you can generally see, again, that the more physical parameters like the euphotic depth, the mixed layer depth, and the depth of the observation are very important for making predictions. And just to kind of show what also comes out from the Bayesian hierarchical model is that you can also see the differences between the instrument level models. So here I've got what I've called the intercept, which is essentially the average flux that you are likely to get from each of those instruments. And what you generally find is that the sediment traps and the thorium instruments tend to give you smaller fluxes than the EVP. You can also estimate the measurement errors from that instrument level model, and naturally we find that the UVP is has less error in it, and naturally that posterior is a lot smaller because, again, as I said, 90% of the observations are from the UVP, and so you have more certainty of that measurement error. So to conclude, we trained models to produce global POC flux maps from the in situ observations and the environmental driver data sets, and we found that the random forest model performed the best, and that the more physical features like the euphotic depth and the depth of the observation and the temperature were the most important for predictions, and that was sort of unanimous with the Bayesian hierarchical model as well. So we trained the Bayesian hierarchical model to account for those data set differences, and generally found that with the sediment traps and the thorium, those are more likely to give you smaller fluxes, which is very useful to send back to the modelers in terms of kind of correcting for that when you're trying to get fluxes from these instruments. And in terms of future work, so firstly, adding that non-linearity into the process model is definitely something that's ongoing, but also doing regional and seasonal models. So we know that seasonality is very important for PAC fluxes. We know that generally the fluxes you get are a lot higher around the springtime due to phytoplankton blooms and other factors. And we also suspect that regionally we're likely to get different relationships with the environmental drivers based on the region that you're in the ocean. So yeah, we'll see what we get from that. So yeah, thank you for listening, and please feel free to ask any questions.
Thank you, Abby. I think we have time just for one quick question from Slido. And the question was, what is the neural architecture that you use for the neural network?
Sorry?
What is the neural architecture?
So an MLP regressor is what we used to start the question they're asking. Yep.
Okay, thank you very much.
Great. Thank you.
So we're going to move to our next speaker, Solomon White from the University of Edinburgh.
Hi everyone, thanks for having me here. This work is based on an extension of my PhD, so forgive the sort of general title. So this is to water type classification to improve model generalization. And the model in question is a model predicting sea surface temperature and salinity from multispectral satellite imagery, specifically Sentinel-2, which has a 10-meter resolution. And these are some of my partners here. Just to sort of imply why we sort of need these products. Coastal environments support the most diverse marine life. In fact, 90% of biodiversity in the oceans is in coastal environments. They're incredibly complex with upwelling, glaciers, rivers supplying nutrients, and because of this, they're very prone to sort of stratification, eutrophication, and with climate change, you get events like marine heat waves, algal blooms, where they can sort of expand very quickly, suck up all the oxygen, lead to sort of dead zones. And an SST and SSS are key to understanding these drivers and understanding like acidification, coral bleaching, etc. And currently, these are not being met by adequate spatial resolution of either remote sensing data or other models. So this is just a median image from Sentinel-2, the satellite I'll be working with in RGB, January 2021 to 2022, and you can see there's a sort of flooding event in the land, and there's a big sediment plume coming out, and you can see that in the above image. The bottom image is a MODIS sea surface temperature image, which is 1 kilometer resolution, and you can't capture this at all, basically. It's just not sort of visible in the image. And even when you look closer, there's a lot of land adjacency effects where we have sort of pixels being classified as land and water, and if you have a pixel that has a little bit of land, and it kind of doesn't sort of perform well. Models also have a similar issue in these kind of regions because open ocean models are kind of on the kilometer scale because that's what we need for the ocean currents, but coastally they don't kind of work. And it's a very complex region because you have interchange of three different interactions. You have ocean, land, and atmosphere, and they all kind of covariant force upon each other. So briefly, what my sort of underlying model methodology is to do. So temperature and salinity don't actually change the observation reflection of the colour of the water itself, but they co-vary with things that do. So you can see there's some sort of physics equations on the left that show that absorption of like chlorophyll and CDOM and backscattering all will affect these water-leaving reflectance. This reflectance is then transmitted through the atmosphere and measured at the top of the atmosphere satellite data. And normally what's done in these cases is we sort of learn these empirical coefficients for these like absorption coefficients on the bottom, and then we sort of perform some radiative transfer modeling to estimate the top of the atmosphere data. But this is introducing two kind of uncertainties, and combine these going through, and also these need to be estimated for each kind of region. So I'm trying to aim to create a sort of globalization model that can be generalized better. So you just take the top of the atmosphere data and you go straight to the temperature and the salinity. So briefly, how this does this? This is some of my buoy training data. So I have 14,000 points in the Gulf of Mexico, quite spread of temperature and salinity. And I take a 3x3 pixel window of the satellite and match that with a ground truth of a buoy and take the medium image. So I know exactly one pixel corresponds to whatever temperature and salinity. I'm building a neural network model, just a simple backpropagation MLP. So it has 15 hidden layers of radio activation and kind of a kind of standard activation system there. So that's what the model is, and as you can see, it's quite a complicated thing because in this case, which is within one bay, you have in one case temperature and salinity inversely proportional, in another sort of very complex variable. So you need this kind of highly complex machine learning model here. So these are some of the outputs for there. So it's nice, and when I've compared it to other validation, there's clear spatial covariance between salinity on the left and temperature on the right, and you can see this ocean front here, which is the kind of colder water and programs to the sort of fresher water there. So that's been picked out by the model quite nicely. But the issue is, and these are some of the results applied to a sub-region which wasn't tested, which wasn't trained on, and it performs reasonably well. You have R squared of above 0.9 and above 0.85 for temperature and salinity, but it's still, the errors are relatively high because it's such a varied data set. So the aim is to try and incorporate, and this is all trained on tabular data, so it's not in spatial information, it's just purely from the satellite data, which I did that to increase the speed of the model application. But the aim is to try and use classification to add in some spatial information to this model to help also like split up these into different sort of sub-regions. So to do this, I looked at k-means clustering, and through the literature and doing some silhouette analysis and elbow methods, I decided that 10 clusters was the best. The plot on the right shows the different spectral bands, the sort of split, the grouping of these fuzzy k-means of each cluster, and this sort of shows the kind of spatial regions of locations of each of the different clusters. So the kind of the importance in here is, I'll go to this slide, you can see that we have the spectral change of this sort of average spectral range for the overall bands, and then for each different region. And then you can see how the actual distribution of the temperature and the salinity changes with each of these. So salinity changes a lot more because salinity is directly related to CDOM or other chlorophyll metrics. Temperature has less of an impact, but it's predicted quite well with the infrared regions there. And then these are some of the results again for the test case here, based on taking now cluster information as an input into the model. And so temperature performs very well, and it kind of gets this sort of seasonal cycle here. Salinity still has some issues, but importantly, at least in these cases, it's capturing like extreme spikes. So it's in terms of comparing it to other products, open ocean models have better temperature and salinity, like RMSE results, and can get a lot closer, but they're kind of quite uniform regions. In these cases, particularly in coastal regions, what we're really interested in is like spikes. So is there a extreme temperature event? Is a sort of anthropogenic bleaching coming through, or sort of pollution coming through, and can we kind of detect those there? So then, as I mentioned, this is the sort of then applying this to the initial satellite image to try and capture the net spatial neighborhood information, because clearly if you have upwelling, eddies, fronts, or in this case river plumes, they're going to have neighborhood information linked the spatial covariance between them. So this is two regions here, and you can see we sort of have kind of like open ocean, turbid waters, and mixing layers here. And then this was then applied to the this cluster class is then assigned as an extra input to the model and then applied through there. And the further advantage of this is basically means that you can apply the model to regions where it hasn't been trained and against water types it hasn't seen before, because it might be for example, here I have in Mexico, and then I have some cases in like the UK. And if you have a sort of warmer region that's a particularly cluster type of water type in Mexico, which is more common, then when you take that and apply the clustering class to the UK, then it sees the same water class and then can sort of estimate and sort of it increases the generalization ability there. And then finally, these are some of the results just in terms of, you can see there's a clear correlation with cluster against sea surface temperature. And you can see that sort of you can kind of come through there. Yeah, thank you.
Thank you very much. Do we have questions in the room? Yeah. I'll give you my mic.
Hey, very nice talk. I was just wondering, when you make these clusters, how do you decide how many you need?
Yeah, so that was basically based off, there's like different metrics for doing k-means clustering. So I did like silhouette analysis and then looked at the elbow method. And as well, there's been previous literature for water optical types, which has been like 13 for land and ocean, and then less, and then I sort of picked, so that's why I kind of picked 10 based on that.
Maybe one last question.
Interesting talk. About your clusters, when you cluster them, have you analyzed those clusters for spectral signatures and their relationships with the physical processing that bounds each cluster?
Sorry, how do you mean? So I think the plot showed the
yeah,
for each
but
cluster,
the signature seems quite close, right?
Yeah.
So what do you feel about the physical processes? Is it sufficient enough to deal with the spectral signature, or would you think on other strategies to enhance this kind of separability, kind of a motif, for example?
Yeah, no, I think so salinity does better. Temperature is kind of a bit too close. I think this is kind of a problem throughout the research, because I was like, I could include like bathymetry, tidal information, location data. I try to not include that to keep it as generalizing as possible. So then you could take literally an image and then apply it somewhere where it hasn't seen, because it's not learning any other information, because location doesn't do that. And also for speed. But then if you do input those, then you do actually get an improvement in terms of, so it's kind of the trade-up between the two of how much you want it to be in one region versus being able to put there.
Thank you, Solomon. So now to finish this session, we're going to have a recorded talk by Peter Manshausen. Yeah. Yeah.
Hi everyone. I'm going to present on my research about predicting visible ship tracks. Let's start right away with what is a ship track. You can see this picture in the background of the North Pacific, and there are these long lines of brighter clouds, and those are where ships have polluted the cloud and increased the cloud brightness. And this is what we're studying here. Some background. So ship tracks have been used for a long time for studying aerosol cloud interactions. However, more than 99% of them are not visible. So on 99% of the cases, a ship goes over the ocean and the aerosol doesn't cause the cloud above to be visibly brighter. And this introduces a sampling bias into the studies of ship tracks. So finding out what makes a ship track visible could help to address this. Also, finding out what causes visible ship tracks is in a way finding out when clouds are very susceptible to aerosol. And this is of interest if you're interested in geoengineering. Now, just a very brief overview of aerosol cloud interactions. The main idea is that if you have a cloud like the one on the right with the big droplets and you inject aerosol, that will reduce the droplet size. And this is important for albedo. What happens then is kind of less certain. You can have either a suppression of precipitation, which increases the liquid water in the cloud and increases the albedo, or you can have enhanced evaporation, which decreases the albedo. So here we compare two data sets, one of advected emissions, where we use ship positions and the winds to advect the emissions of the ships to the time that we have a satellite overpass. And this gives us an indication of where clouds were polluted by aerosol. But as I said before, often this will not mean that there is a visible track. So this is a data set of all the clouds that potentially could show a visible ship track. And then we have a data set of ML detected ship tracks. So those are the ones that are visible in satellite imagery. And these are given by these polygons that you can see on the figure. And what we do then is we overlay the two of them and basically ask the question, how many of these points of advected emissions are within these detected visible tracks and under which conditions? Now we can ask the question, when are they particularly likely? When are they likely to overlap? And we see that there's a strong seasonal cycle, and we also see that there's a large regional dependence. So we have a lot of ship tracks, a lot of visible ship tracks in the austral winter. So the ticks here are in June of the year. So we always have a peak in July, August, and we see a peak in the stratocumulus regions of the southern hemisphere. Now this dependence on time and space means really that there is a physical reason for visibility, and that needs to be encoded in the meteorology of these regions. And so what we do is we add some more data, some reanalysis data, to predict visibility or invisibility of tracks. We also add some satellite cloud properties of these scenes, and then we use a random forest to classify scenes into visible day scenes or invisible day scenes and train with the data that we have. Now, it is quite hard to predict this. Our scores are only okay-ish. We get relatively high precisions and recalls in the majority category, the invisible track category, and we get relatively low performance in the visible category. There's a challenge of class imbalance. Now we restrict the data only to those high visibility regions, which brings us from 1% of visible tracks to 25% of visible tracks, but this is still kind of a minority class. There also might be a problem of not having enough information on the processes on small scales in the reanalysis data, because that comes at 25 kilometer resolution. If we trust the model a little bit, we can back out the importances of different features. So what the model uses to make its decision about visibility or invisibility. And the way to read the SHAP value plot here on the right is to look at the variable you're interested in. So let's take the one that it thinks is most important, RH 850, relative humidity at 850 hectopascals. And then look at the color. So the color indicates whether it's a high or a low value of that feature. So a low value would be dry. And where it is. So right indicates it's a positive impact. In our case, 1 means visible, 0 means invisible. So the right half is a visible day, left half is invisible. And then we can also see the distribution just by the violin thickness. And this indicates that RH 850 contributes to visibility if it's low, if it's dry. And in the same way, we will observe low sea surface temperatures, low boundary layer height, high cloud cover, and a stable lower troposphere in these conditions. One challenge that we're facing is that this does not give us any information about causality. So in our case, our important features are almost all correlated with each other, and it's because sea surface temperatures are causing these other features. So low sea surface temperatures are the physical origin of these. Only the vertical velocity at 950 hectopascals, so the surface vertical velocity, is relatively uncorrelated to the others. In summary, we found out what favors the development of visible ship tracks versus invisible ship tracks, and we hope this will help assess the bias of ship track studies for aerosol cloud interactions. We show strong seasonal and spatial variability and find a specific meteorological regime that is characterized by low sea surface temperatures, high cloud covers, shallow boundary layers, and dryness above cloud. And that concludes my talk. I'm sorry I can't be here in person or even at the same time, but please reach out via email if you have any questions. I'm also currently working on a different really cool project on data assimilation with diffusion models, so if you're interested in this, also please get in touch. I would be really happy to chat. Thanks very much for listening. Bye.